I just want to continue the derivation of two more Michaelis-Menten plots. So now last video we've probably seen already two of their plots, which is one of them is the double reciprocal plots, and I believe the other one was plotting V by S against S. Now, and we also figured out what actually didn't work. Yeah, so we did V against V by S, and that was like by multiplying the denominator to the left hand side, and we just invert the equation. That linearized it. So let's try one last method of linearizing the plot before we move on to something a little more complicated. So anyway, we can shift this S over. We divide everything by S. And when this is the case, we can start to invert. So in the previous videos, one of the methods was just to invert this whole equation by itself. The other is that you multiply by the bottom and then invert. Now we are dividing by this S substrate concentration and then invert the whole equation. So these are three of the ways that we can use to linearize the equation. And so we have S by V on the left hand side. So we have Km by V max plus 1 by S, 1 by V max. And so we'll have a gradient, this slope, and this is the intercept. Okay. So you have S by V against 1 by S, and you have a slope of 1 by V max. That will be a positive slope again, and you have Km over V max as your intercept. So in summary, there are three ways to do it, to linearize. So the first way is to invert. These are the two steps you got to remember, at least one or two steps. So just invert everything. Second, divide by bottom. Invert. And third, you have to multiply, multiply. So you multiply the bottom and invert it. And the third way is to divide by S, divide by the top. And invert. Each of these have special names for them. This one is the double reciprocal plot. The last one is called Haynes-Wolff. Haynes-Wolff plot. And the second one is the Eadie-Hofstee plot. So these are three of the plots that we discussed. The linearization of these equations can come under these three methods. Now the last thing we can do is something, like I said, a little more complicated. So let's use this bottom as part of our workspace. And let's start again with our equations. V max into S over Km plus S. And let's say now you want to do some integration. Now how are we going to do that? Well, we remember this equation, right? So V equals to dp dt. That's the definition. Well, let's have it in terms of S. So for every 1 unit of P, or 1 mole of P being created, or rather produced from S, 1 mole of S is consumed. So from this stoichiometric ratio, you can have this. Okay, so we substitute this into the V on top, and you get this equation: ds dt V max into S over Km plus S. Alright, and then we bring all the S terms to the left hand side to start integrating. So we have minus ds over dt, and we are bringing all the S terms on the left hand side. So we have Km plus S divided by S, and then you have V max on the right hand side. So we're bringing this over, and this will be on the right hand side. So multiply by Km plus S, divide by S, and this is what you get. And now we'll bring dt to the right hand side. So you have ds, so this is 1 over, this is Km over S plus 1. So I'm just simplifying this part in the brackets. I'm bringing minus dt over. Okay, so if you have S versus T data, it'll be pretty good. So now let's integrate from S0 to S, and integrate the right hand side by T equals to 0 to T equals to T. Okay, so you have this on the right hand side. So S0 is like the initial concentration, and S is the concentration where, well, at any time T. So this is S at time T. I mean, okay, that's one way of integrating. Of course, you can integrate at maybe T equals 5 or T equals to 10 minutes. It depends on how you want to fit this equation using your experimental data. So okay, let's do this. Km over S plus 1 ds, and we bracket this, and let's integrate ln. Okay, so you have Km plus ln so you have 1 km times, I'm sorry, okay, this is a constant, we bring it out, right? So Km ln S at the time T over S0 okay, plus S at the time T minus S0, and you get V max into T. Okay, so we have like a few variable terms here. So we have this ln term with this st, and then this batch here with also another st, s at time t. Okay, so what we want to do is to reduce the number of experimental data variables into two. So this is experimental data, s at t, and this is also so-called experimental data. So you have a plot of s versus t. You can generate this data, and of course you have S0, which is your known initial concentration. So let's just divide everything by t so that we can have two variable terms, variable terms based on experimental data. Okay, so let's divide everything by t. Okay, so that's the first term. Let's add it to the second term. Oh, This should be a minus S naught over T. Okay, so on the right hand side, it will just be Vmax left. Alright, so we are almost there. So depending on how you want to plot, this thing is more or less it. But let's say you want to have a y and x axis. Let's rearrange it and do something a little neater. So let's have this to be our y variable and this to be our x variable. So we'll divide everything by 1 by k. Divide everything by km. So let's just do that. 1 by t ln st over s naught plus 1 by km st minus s naught over t equals minus Vmax over km. So now it's pretty clear what is on the y-axis. This is the y-axis one. This one's the x-axis variable. So we just shift this to the right and we'll be more or less done with the linearization process. Okay, so I'll probably use the other piece for the next video. Piece of paper. Anyway, 1 by t ln st s at time t over s naught equals minus 1 by km s at time t minus s naught over t minus Vmax over km. And that will be our intercept. And this will be our slope. Okay? So that's pretty much it. So you plot 1 over t ln s of t over s naught, and you plot it against this st minus s naught over t, but you'll get a kind of a negative, very negative graph, as you probably see, because st minus s naught, that will always give you a negative number. So you want to turn it more positive. This is the other thing you can do. Let's swap the positions of the central variable. 1 by km s naught minus st over t minus Vmax over km t ln st over s naught. And you also kind of figure that the right hand side is going to always be a negative number, because st is smaller than s naught, so ln of a number less than 1, that will give you a negative number on the left hand side. So if you don't like working with negative numbers, you can do this instead. So we'll just swap the locations here, and then we'll have a negative ln. That will be equals to 1 by km s naught minus s at t over t minus Vmax over km, and 1 by t ln s naught over st equals minus 1 by km S naught minus bracket ST over T plus V max over Km. So if you just zoom out, you can see that this is a nice positive number now, and this is also a nice positive number. So you're plotting a positive number against a positive number. That gives you a very nice graph. And that is it for the batch. This is the last way we use integration, and this is quite suitable for batch kinetics. Okay, and that's the summary of how we can turn Michaelis-Menten plots into something we can linearize and plot on a graph, so that we can extract data for Michaelis-Menten constants and the Vmax based on regression. So that's all I have for you in this video. Thanks for watching. It's a bit messy, but hope you get the ideas you need to get. And I'll see you guys next time. Now, if you want me to have a better remake of the video or something, you can leave a thing in the comments. I'll see if I can redo this if I have a little more time. Ciao.